Hey PStats! Today we're going to take our first look over at density curves, and we're also going to take a first look at a really important density curve, which you may have heard of before, and is really a backbone of AP statistics. So let's get going here with the next screen and exploring density curves. So this is a set of experiments that you're supposed to do in class, and we'll do a few of these together. We're going to complete each of the following experiments and submit our answers using a Google form. We're not going to do that today in this video. That's what we would do in class. And you're going to resubmit your answer a total of 3 submissions, and then you're going to predict what the graphs of the class data is going to look like if we did this many times. So more than just the 30 or so people that are currently in class. We're going to do this many times. We're also going to draw and label lines where we think that the mean and median will be. Experiment 1 is to roll the die and record the value that it lands on. Well, this is pretty easily done if we go to Google and just do virtual dice. You don't even need real dice. And we're going to roll a 6-sided die. We're going to, well, no, we don't need 2 of them. We're just going to roll this one 3 times. So let's see what we get. We get a 2, 4, and a 4. So let's make our prediction. What do we think that if we roll dice many times, the way I like to think of it is one value going to be systematically appearing more than others? So if we had a fair die, would we expect to see a lot of 1s and not a lot of 6s? Or maybe we expected to get 1 a lot or 6 a lot and not a lot of 1s? Or maybe, something crazy, like maybe we expect that the die will land on 3 a bunch of times. And based on what I'm hearing, you probably expect that none of these outcomes are going to be systematically favored. So if no outcome is systematically favored, well, that would mean that all the outcomes have the same frequency. So we would expect something in the long term to look like this, with all the probabilities going to 1/6. Now, in actuality, what would it look like? Well, it probably wouldn't be everything at the same height. We would probably get something a little bit messier, maybe something like this, where everything is not exactly at 1.67, and maybe, here we have 2 and 3 are favored a little bit more, but not crazy more than the other outcomes. So in both of these, we would call these uniform distributions because the frequency of each outcome is about the same. And for both of these, the mean and the median should be right around the same place. Now this is kind of textbook symmetric. I know we talked about symmetric distributions before, but symmetric means the left side and the right side are about equal to each other. And that's exactly what we see here. So in both cases, the mean is about equal to the median. Now, one thing we could also talk about here is if we have this perfectly uniform distribution, then really the height of all of these should be about the same. And since the area underneath this distribution should be 1, then each of these heights should be 1/6. Whenever we try to represent area and probability as the same thing, like we're doing here, area and probability are the same, we call the resulting curve a density curve. And because it's related to area, we say that the area underneath the density curve should be equal to 1. Now there's another thing that I'm also kind of dissatisfied here with these density curves, is that in histograms we shouldn't see any white space in between any of these bars. So I'll try and fill that in later, but you should know that watching the video that there should not be any white between the bars. It should all be like an actual histogram. So let's move on to this one. We're going to take a look at experiment 2. We're going to try and toss a penny and make it land on the target. So this is something that we did in class a few times. And there was those results. Well, those kind of look like this. So in the ones that we do in class, we try to toss a penny into a circular target that's about 50 centimeters away from the person tossing. And this is a result from one person. The first time they did it, they got a 59. Second time, a 63. Last time, they got a 60. So what would we predict this to look like? Well, I'm thinking, first of all, that this person isn't a very good indicator because they were off on all 3 of these. But you would expect a lot of people to be close to the target. So the kids in class, they like to say that they're really good at throwing the penny into the target. So we would expect a lot of students, a lot of the kids in the class, to get close to the target, and very few of them, if any, very far away from that target. So we would expect to see a right skewed distribution. And you'll notice here we've got a lot of people who are within 3 centimeters or 3 inches of the target, and less people further away from the target. And in this case, where would we expect the mean? Well, that's probably less difficult than figuring out the median. The median here would be the place where the area to the left, the proportion on the left, is equal to the proportion on the right. So that would probably be right about maybe here. No, maybe a little bit further. So maybe right about here. Now, the mean probably should be a little bit to the left here. Now, if you think about the mean, you're thinking about the balancing point of this. Where would the left and the right balance? And so we would probably put the mean over there. What actually happened? Let's take a look at a histogram of what actually happened in class. What actually happens is, yeah, it's a right skewed distribution. Now, it doesn't look as nice as this nice smooth distribution, but yeah, this is definitely a right skewed distribution. And of course, the mean and the mean and the median probably stack up very similarly to what we thought, with that median at 21.25 and the mean at 35.75. So the thing I want you to notice here is this is a right skewed distribution. In a right skewed distribution, the median is less than the mean. In other words, the mean is on the right side of the median. And do you think the opposite's true for left skew? Well, yeah, it's true. The mean is to the left of the median in a left skewed distribution. So that kind of gives us more meaning to decide about what left skew and right skew really mean. Now for exercise 3, we have a distribution where we're trying to stop our stopwatch at exactly 5 seconds, and we're supposed to record what time the stopwatch reads. So let's try one of these. With Google, you just need to type the word stopwatch and it gives you a virtual stopwatch. So I'm going to close my eyes and count to 5. So we got 0, 1, 2, 3, 4, 5. So I'm at 5 seconds and 5.39 seconds. Let's put that in my worksheet. And we'll also do a couple of other measurements. So I got 5.39, 4.28, and 5.24. So this time when we make our prediction, what do we think the class after many repetitions would be? Well, when I think about it, we're going to get a lot of answers that are close to 5, a few answers that are less than 5, and a few answers that are greater than 5. In fact, I couldn't say that people are going to favor, or there will be more people measuring above 5 than less than 5. So when I envision what this is going to look like, I'm picturing a distribution that looks like this. Now in this distribution, we would have a mean and a median right about at the center because it is symmetric. And that mean and median equal to each other would be right around 5. Well, what did it actually look like when we did this in class? Well, we got an actual distribution that looked like this one, with a median at 503 and a mean of 4.98. So really close, which should indicate some degree of symmetry in this distribution. So what we would call these are approximately normal distributions. Now that's normal with a capital N because it is this specific bell-shaped curve. Now a few things about the bell-shaped curve that you should know. The bell-shaped curve definitely has an inflection point right over at the shoulders here. Let me highlight that again. It has an inflection point right about here. And it goes from, if you're in calculus, you know that this area right here is concave up. And over here, we got another concave up section. And right in the middle, we have concave down sections. So the tails turn up at the ends. So I don't want to see you draw a curve that looks something like that. That is not a normal distribution. A normal distribution has inflection points. It keeps on going, kind of like that. All right, so here's what we're going to do over here. This is a normal curve, and we're labeling the values of 1, 2, and 3 standard deviations above the mean using the stopwatch data. Now, we already said that the mean was 4.98. So we'll put a 4.98 right in the middle. And I can tell you, looking at the distribution, that standard deviation was 0.27. So since we use a normal distribution a lot, we like to abbreviate that with capital N, 4.98, and 0.27. So what we're going to do next is we're going to mark off on our chart one standard deviation to the right. So let's think, how much is 4.98 plus 0.27? Hopefully you said 5.25. Now let's add another standard deviation. What's 5.25 plus 0.27? That gets us 5.52. And we'll do that exercise one more time. 5.52 plus another standard deviation will be at 3 standard deviations, and that's 5.79. So the time that is the mean is 4.98. 1 standard deviation above the mean is 5.25 seconds. 2 standard deviations above the mean is 5.52 seconds, and 3 standard deviations above the mean would be 4.98 plus 3 times 0.27, or just 5.79. Now we can do the same thing by going below the below the mean. So 4.98 minus 0.27. That's 4.71. So 4.71 is 1 standard deviation below the mean. Subtract another 0.27. That's 4.44. So 4.44 seconds is a time that is 2 standard deviations below the mean. And we'll do this one more time. Now we got that 4.17 is 3 standard deviations below the mean. So every time that was done by a student can fit into one of these categories, either between a standard deviation of -1 and 0, or maybe a standard deviation of 1 and 2, or 2 and 3. And we can just count now what percentage of the data was within 2 standard deviations of the mean. Now, counting from the data sheet, which you don't have, but I'm taking a look at. So 26 out of the 27 in the class, that would be about 96.3%. So if we have that, what percentage of the data is further than 2 standard deviations? So basically is not between 4.44 and 5.52. Actually, before we do that, let's take a look at what that means to be within 2 standard deviations. So if you're within 2 standard deviations, that means your time falls into this yellow area right here. Okay, so these are all the times that are within 2 standard deviations of the mean, either greater than -2 and less than +2. By contrast, anything in this blue area is more than 2 standard deviations away from the mean. So anyone who had a time that was less than 4.44 or greater than 5.52 would be outside of 2 standard deviations. Now my data says that that is 1 out of 27, which is 3.7%. Now remember how we said this data was approximately normal? That's because this is slightly different than what the numbers should be for exactly normal distributions. So for an exactly normal distribution within 2 standard deviations is 95%, which means further than 2 standard deviations, that would be 5%. Okay, let's take a look at the next one, which would be what percentage of the data is greater than 1 standard deviation above the mean. Taking a look at the normal curve, I can highlight greater than 1 standard deviation above the mean, and that would be this region right over here. Anything that goes from 5.25 all the way to, well, whatever the highest number that we have. Based on what I got from the class, that was 5 out of 27, or about 18.5%. What would that number be in an exactly normal distribution? In an exactly normal distribution, that number should be 16% greater than 1 standard deviation above the mean. And then how about between a z-score of -2 and -1 and +2? Let's see what that looks like. Let's see, between a z-score of -1, which is right here, and +2, which is right here. So we're looking at times that are between 5.52 and 4.71. What does the data say that is? Well, my class got 24 out of 27, and that's about 88.9%. Now, in an exactly normal distribution, that number would be 81.5%. So you can kind of tell, since our numbers are not exactly equal to the normal distribution, this distribution of stopwatch times from the actual class isn't exactly normal. And that's why we say it's approximately normal. No distribution will ever be exactly normal if it's taken from real data. So it's important that you notate things as approximately normal rather than exactly normal. And that takes us to our big ideas for this lesson. So what are the big ideas of this lesson? So first of all, we had this idea about density curves. Now, in a density curve, the area between 2 values and under the curve, the area is the same thing as probability. The area under the entire density curve, therefore, needs to be 1, or 100%. When you're dealing with a uniform density curve, then if the length of the uniform density curve is k, the height is just going to be 1 divided by k. And that's some mathematical consequence that kind of allows us to, or that comes from the fact that the area needs to be 1. Secondly, if we're taking a look at left and right skewed distributions, the left skewed distribution is always going to have the mean to the left of the median. And then in a classically right skewed distribution, the mean is going to be to the right of the median. Distributions that are symmetric will always have the mean, median, and the mode actually equal to the same number right in the smack dab in the middle. And then learning target number 3 here is something that we call the 68-95-99-7 rule. Now, in this rule says that 68% of all data in a normal distribution is within 1 standard deviation of the mean. 95% of all data is within 2 standard deviations, and 99.7% of all data is in between 3 standard deviations. Now, you can also take advantage of the fact that the mean and the median is the middle of the data, so anything below the mean is 50% of the data. Anything above the mean is also 50% of the data. So for example, this part that I'm highlighting, this is all 50%. And if the data is symmetric, that means within 1 standard deviation is between a z-score of -1 and a z-score of 0, that's about 34%. So because half of 34, or half of 68 is 34. Also, that means that within a z-score of -2 and a z-score of 0, that's going to be half of 95. Half of 95 is 47.5. So this green area here represents 47.5 of the data. Also, the area at the end of that is going to be the complement of that. 47.5 from 50 is 2.5. So this yellow region that I've highlighted is 2.5% of the data. Now, mastery of this rule is going to allow you to calculate probability for a lot of different regions just by using addition and subtraction and a little bit of cleverness. So really get well acquainted to that 68, 95, 99.7 rule, and we will begin with our check your understanding. An internet reaction time test asks subjects to click their mouse button as soon as the light flashes on the screen. The light is programmed to go off randomly after a selected time. The density curve models the amount of time that the subject has to wait for a flash. What height does this density curve have to have? Well, taking a look at the density curve here, this density curve has a width of 4. And if that density curve has a width of 4, then the height needs to be 1/4. So the height of the density curve should be 1/4. How about number B? Ooh, sorry about that. About what percentage of the time will the light flash more than 3.75 seconds after the subject clicks start? So 3.57, let's figure where that is on our density curve. So if 3.75 is right about here, this looks to me as though that yellow rectangle has a width of 1.25 and a height of, well, the height is still 0.25, 1/4. So the area is 31.25 or 31.25%. Now let's calculate and interpret the 38th percentile. So the 38th percentile would mean that the area to the left has got to be about 0.38. So if I estimate 0.38, that's about a third. That's going to be about this area right here. So somewhere around 2.4 maybe. Well, we can calculate that actually. I know the area is 0.31, and that's equal to the width multiplied by the height, because we're looking at a rectangle. Well, the height is 0.25, and that tells me that the width of the rectangle should be about 1.52, the blue rectangle over here. Well, the blue rectangle starts at 1 second, so the time here, right at the edge of the blue rectangle, that's got to be at 2.52. And if you remember our interpretation, what we're saying is about 31% of our... Why am I doing 31? It should have been 38. Let's just do 31. 31% of the light flashes are at or before 52.52 seconds. Sorry about that. I don't know why I'm reading these incorrectly. Let's fix those now. Luckily, by magic, the other numbers are correct. So about 38% of the light flashes are at or before 2.52 seconds. Okay. Let's see now question 2. That takes care of it for the light flashes. The distribution of heights for young women age 18 to 24 is approximately normal, with a mean of 64.5 and a standard deviation of 2.5 inches. So let's sketch a normal curve that approximates the distribution of young women's heights and label the mean and points that are standard 1, 2, and 3 standard deviations from the mean. Now, I personally have a normal distribution curve that I like to use a lot. It looks like this one that you see here. And we're going to label the bottom with those heights. So the mean height is 64.5. And we'll just keep adding 2.5 inches. And then we'll go the other direction with subtraction. And that takes care of labeling our normal curve. The other thing we should write here is our notation that we're looking at a normal curve, 64.5 and 2.5 for the standard deviation. Okay, about what percent of young women have heights that are less than 69.5? All right, let's highlight that. Less than 69.5 is going to be right over here. This shaded region here. Now that's most of the curve. The only part of the curve that's not highlighted is this part right here. So maybe it's better off doing this by subtraction. Well, here we've got the blue plus the yellow is equal to 50% of the curve. And from the 97 part of the rule, we know that the area between 0 and 2 standard deviation is half of 95, so 47.5, which leaves 2.5% of the area for the yellow if the blue and the yellow have to add up to 50%. Taking away that blue region, that yellow region is still 2.5%. And now the entire curve has to add up to 100%. So the green section, well, that has to be 97.5% of the area. So what proportion is less than that? Well, that's going to be 97.5. Let's show some work here. The appropriate thing to write would be the proportion or the probability of heights that are less than 69.5. That's going to be the proportion on the z-curve that's less than a z-score of 2. Remember, 69.5 corresponds with a z-score of 2. And that's 1 minus that 0.025%. And that's 97.5%. Okay, is a woman that is 62 inches unusually short? No, 62 inches would just be right about, well, no, it would not even right about, it is exactly at a z-score of -1. So that's not very unusual. So a young woman with a height of 62 inches is not unusually short. 16% of women are shorter than her. And we talked about how to get that 16% using a z-score of positive 1 and 34% between a z-score of 0 and positive 1. We just need to transpose that to the left side of the curve. So between negative 1 and 0 is also 34%. So that does it. That was a lot of really important statistics work on our lesson today. Good luck, and we'll see you next time. Don't want to delay you any longer. Have a good one.